Thank you, and please welcome Jennifer Gardy and Maddee Nash.
Hello, everyone. Yeah.
Hello, Cleveland. Yeah. Great to see you.
So no, we're not going to be singing, but we are going to be having a really interesting conversation today with Dr. Jennifer Gardy from UBC. So thank you so much for being here.
My pleasure.
Such a treat for me to come back to GISS. So thanks to Michael and George and everyone on the Salt Spring Forum board for having me back. So let's get started. So you are a self-proclaimed disease detective, and you're working in British Columbia at the Centre for Disease Control.
Yep.
So why don't you tell everyone what it means to be a disease detective and what kind of work you're doing at the BC CDC?
Sure. So I spend about, I'd say 3/4 of my life doing straight-up science medical research. We'll talk about science communication in a bit, but my life at CDC is really being a disease detective, tracking outbreaks of infectious disease, figuring out how they start, how they spread, and most importantly, how we can use that information to control them. So a lot of people don't really know what the field of public health is, because when we do our job right, you don't know. You're not getting sick because we've done a good job. But I always kind of like to explain what I do in terms of zombies and a zombie apocalypse. Out of curiosity, how many of you have ever thought about what you would do in a zombie outbreak? Who has a plan? Hands up, who has a plan? Who's at least thought about what their plan would be?
Who has the emergency kit in their
Exactly. Well, BC CDC is the agency that, were there to be a zombie apocalypse, we're the ones that would keep you safe. So the types of work that we do, you try and figure out what's causing this outbreak of zombie-itis. Is it a bacteria? Is it a virus? Is it a fungus, a parasite, or something? How can we diagnose it and figure out who's infected? How is it going to spread? Can we develop models that show how quickly this disease will move through a population? Can we develop models that say, okay, if we try this defense technique, is it going to work out or is it going to fail? And we work on developing therapeutics as well. We say, okay, what can we do in terms of treating zombies? How do we, once you've been bitten, what can we do for you? Yeah. So it's kind of all the things that you'd see in a classic zombie film if you were, looking at what the CDC were doing in a movie like that. But we're doing kind of the same thing, just on less dramatic scale. So instead of zombies, we're talking about things like tuberculosis, influenza, measles, mumps, salmonella, food poisoning, you name it. So my work there is really all about understanding how are these diseases getting into our population, how do they spread from person to person, and how can we make better public health programs to keep our population safe.
Well, it's really interesting work being a disease detective, and hopefully you don't have to protect us from the zombie apocalypse.
I'm on it, though. If it happens, I'm here.
And you have a really interesting background where you've done work on TV and as a journalist, and we were talking last night over a nice dinner at Antipestos about how science is also inherently a very creative discipline, and I think that's maybe not that clear to people why that is. So maybe you can explain sort of how your skills as a journalist and working on TV and doing communications work, how that informs and helps you as a scientist, and what makes science creative?
Yeah. So the other 25% of my time when I'm not being a disease detective, I do a lot of science communications work, and that's been going on for about 10 years now. It started off with a lot of science writing, doing freelance newspaper and magazine articles, just talking about different scientific topics. After a few years of that, I realized that if writing about science was X amount of fun, then talking about it on television was probably 100x the amount of fun. And so I decided to get involved in science television. So I've been doing a lot of stuff for CBC since, I guess 2007 was the first time I started working with them. And it's been really interesting to see, as a science communicator, somebody who's out there telling science stories, it's really fed back into my scientific career in a way that I didn't really anticipate. And it's made me realize how important things like storytelling and creativity are to the scientific enterprise. So you might think of biology, medicine, physics, mathematics, computer science as these very logical subjects that kind of Spock on Star Trek, very very sort of objective. But in fact, I think the best scientists, the best researchers are people that can really pull inspiration from a whole bunch of different fields. So somebody that is very, very skilled in computer science, but is also a really amazing visual artist, for example, can put those things together in really creative and interesting ways. And people that can just cultivate a sense of curiosity and cultivate an interest in other disciplines, you can sort of pick and choose little things from other fields and have that tie back into the work that you do scientifically. So the particular bit of science that I play with is using DNA analysis as a tool to track who exactly transmitted disease to whom. We try and build little maps of what an outbreak of infectious disease looked like so that we can better understand it and prevent the next one. But to do that required not just skills in public health, it required some microbiology, it required some computer science, it required some statistics, but it also required things like a bit of social psychology and social network analysis and understanding the connections between people. It required understanding how to communicate really complicated information to people so that you could explain to folks, this is what's happening in this outbreak. We use really complicated techniques to arrive at this answer, but here's what you need to know about it, and here's what you need to do about this. So it's a really cool example of just all of these different threads that weave together into one really beautiful story in the end, but it came about through thinking creatively and thinking laterally.
Yeah, I think that's what makes public health, specifically global health, such an interesting area because it's so multidisciplinary.
Yeah.
And I think that's something it's interesting for students to know too when they're interested in the health sciences. Medicine is sort of only one dimension of that,
Yep.
but it's the most talked about. So I think it's great for you to explain, to people what is public health, global health, and what are say maybe an interesting question is, what are sort of the qualities that you think make someone good in this area? And so if students are thinking about what they want to do next, what they want to study,
Yep.
What might be good, what might say that they would be good in this area?
Yeah, public health and global health, it's really all about caring for the people around you and making sure that everybody is healthy, happy, well, and everybody has the same access to services no matter where you are in the world. So first and foremost is that compassion, that desire to really help. Second of all, I think it's curiosity. And oftentimes, as you said, people that are considering a career in health just see doctor as the end goal. Like, I got to go to med school and I'm going to become a doctor. And there's a lot of care involved with being a physician, a lot of understanding how to relate to people.
One-on-one.
Yeah, but there's also a lot of memorizing. Yeah. So if you're somebody that's not so much into memorizing and you're more into discovering and the curiosity side of things, creating. It's all about the research side of the medical profession, and that's where a lot of really cool stuff in public health and global health unfolds. And it doesn't matter whether your background is more in the arts and humanities or social sciences, or whether it's in the very sort of hard applied sciences. There is space for everybody. If you're somebody that really likes tinkering with robots, for example, you could build an automated tiny microscope that can go into places where people can't ordinarily afford microscopes. So you can diagnose infections with this cool little tiny device that plugs into a cell phone, and you've got a mini microscope on the spot. So we need engineers to design things like that. Then we need people that just talk to other people. We need people that have those really good interpersonal skills to really understand what's happening in this community. How can we make this community a happier, healthier, safer place? So from one end of the spectrum to the other, there's room for everybody in our field.
I think that's a really good point, and something that's maybe just not that obvious to people. I know, especially me being here, it was not something that I really learned about research and sort of these more sort of nuanced aspects of science until I got to university. So I think that's something to keep in mind when you're figuring out what you want to do next. And I think we're going to open the floor to some questions.
For sure.
Because I think that people will have a lot of things that they want to ask you about. So I don't know, do any students, especially students, but then also everyone else in the audience have a question? I see one there. One sec, we got a mic.
We got a microphone coming to you.
Hi.
Is the mumps the disease that you get like a mump on your neck?
Yes, the mumps is the disease that you get the bumps on your neck. We call it parotitis, and that's an inflammation of your salivary glands, basically the parts of your body that make spit in a mumps infection get really puffy.
You can't eat sour candies, right?
What's that?
And when you eat sour candies, it hurts, right?
Oh, sour candies? What was that?
Sour
Oh, sour kids. No, eating those won't give you the mumps, but it make you feel a little unusual there.
Yeah, right. You don't see many of the mumps these days because we have a vaccine against it.
We have been, there's a mumps outbreak. It came back. Starting in BC, I guess about 2 years ago, we started to see an increase in cases. And mumps is it follows a strange period of about 6 years where you'll get quite a few infections and it'll disappear for a while, and then you get quite a few. So we think we're kind of in one of those periods where you get quite a few infections. But this is a really nice sort of story about how so many threads of public health come together to give you an answer. So about 2 years ago, when it started coming back, and everybody was wondering, well, what's driving this? Is it that periodicity? Is it something, is the vaccine, do we have waning immunity? Oftentimes you need booster shots to keep your immunity up at the original levels. So we did a little bit of genetic analysis, and some colleagues of ours in the United States did a little bit of mathematical modeling analysis. And when you put the two pieces together, it seemed to indicate pretty strongly that you get what we call waning immunity, that over time, the shot that you received gradually loses its power, and at about age 27, we were able to, our colleagues in the States figured this out, and they pinpointed it, like age 27 is the perfect time for a booster shot. So as a result of all of that work and all these different threads and stories coming together, just about 3 months ago, North America changed their recommendation on giving a third dose of the mumps vaccine. So it was a really cool example of the work that you do directly, within a few weeks, leading to a change in policy. And that's a really cool part of public health, is seeing the work that you do translate into change. You go, wait, we did that.
Yeah, that's something that I really like about this field too. You're very close to sort of often the end user, and the research that you do will get translated into to policies and laws and things that actually change the health of people in your community and in communities around the world. Thanks, that's such a great question. Anyone else?
So I'm back there.
Thank you.
I wondered if you could comment on the rise of disease infections that we thought were not that much of a problem. So here I'm thinking about strep A and the rise of also global vectors with people traveling all over the globe now.
Yeah, it's a really interesting time to be studying infectious diseases right now. So we've got a category of diseases that we call emerging infectious diseases, ones that are relatively new on the scene, and we also have what we call re-emerging infectious diseases, things that have been with us for a long time, but just due to changes in our planet, changes in the way that we as humans live, are kind of coming back. And the number of emerging and re-emerging infectious diseases has been steadily ticking upwards every decade since the 1940s, when we've been keeping track of these things. There was a great paper probably about 10 years ago now, that said over a 50-year period, 335 new or old diseases wearing a new disguise popped up on our radar. And that's even after accounting for us just being better at finding these diseases. So we're seeing a lot more. And I think the drivers are really our changing planet and the way we as humans use our planetary space. So we're seeing a lot of new viral diseases spilling over from animal populations. If you want to find where a new disease came from, something like Ebola, something like Middle East Respiratory Syndrome or SARS, it's pretty much a safe bet that at some point it was in a bat. Exactly, it's always a bat. It's always a bat. And it's interesting because you've got these animals. Bats have been just hanging out in the forests, in the jungles, doing their own bat thing. They carry these viruses. They're kind of like little flying airships full of virus, but it doesn't make them sick. The bat immune system can just deal with these things. But they'll start pooping, they'll move into areas that they weren't in before. Oftentimes, people will have, say, like a palm forest, and this is agriculture that they've been using to support their family. They've been growing, date palms or bananas or something, and then they decide, well, I'm not earning as much money as I would like. I'm going to cut down my palm trees, and I'm going to put up a pig pen, and I'm going to raise 2 or 3 pigs to sell at the market per year instead of farming this grove of palm trees.
Danger.
Yeah, exactly, because the bats, they were eating the bananas, they were eating the palms. Now they're flying over a pig pen. They're pooping. The feces from the bat that contains these viruses is landing on the pigs and into the pen, and the pigs start to get infected. And the next thing you see is the people that take care of the pigs, the farmers, the veterinarians, the people working in slaughterhouses. They start to show signs of an infectious disease. And then very quickly it starts to spread from human to human. We call this spillover, and this is happening more and more and more with more of these pathogens. Same thing is happening in the bacterial space, where the way we treat certain bacterial pathogens is getting rid of some, but allowing others to move in. A great example of this is a disease we call invasive pneumococcal disease, IPD for short. And we have a vaccine that can prevent 13 flavors of IPD, but there's many more flavors out there. And so we got rid of those 13, but then another, 10 or 20 crept in to take their place. So we're always kind of in a battle against the bacteria.
It's a tricky ecosystem.
It's a very tricky ecosystem. And we're in a battle against our planet constantly wanting to kill us, it seems. There's a lot of really interesting diseases out there. And when we mess with our planet, the planet messes back with us.
There you go. Thank you.
That was a great question.
Any other students? Oh, yeah, right here.
The microphone is coming.
Thanks, Fraser.
Hi, yes. So, out of all the diseases you've studied in your line of work, which one have you been most interested in? Which one has been the most interesting to work with or discover?
That's a great question. And it's probably Maddee's favorite too. I know it's Kevin Patterson's favorite. Tuberculosis, I think, is one of the most interesting diseases out there. And it's interesting for a lot of reasons. It's interesting because it's an ancient disease. It's been with humans for tens of thousands of years, it looks like. We see evidence of TB in ancient mummies, in their bones. So this is one of these old diseases. And you think we would have got a handle on it by now, but we haven't. A third of the world's population, 1 in every 3 people, has the TB bacterium sleeping inside their lungs, which is an amazing figure. To think that a third of the world's population has this quiet form of this infection. It might never turn into active disease and make you sick, but that's pretty amazing. And it's a disease that we shouldn't have anymore. We have 250 cases a year or so here in British Columbia, and those are 250 cases that we shouldn't have. We should know better. We should know what to do. We should be able to prevent TB transmission. We should be able to prevent the sleeping germ from waking up into the active disease, but we haven't yet. We're getting closer, but we're not really there. So I think it's a really interesting and important problem, and it's just a fun organism to study. The type of work that I do is easy to do with TB. It's harder with some other bugs. Another question I get a lot is, what's the scariest disease out there? Which one are you most terrified about? And for me, the answer to that question wouldn't be a specific disease. It wouldn't be, rabies or Ebola or something like that. It would be a phenomenon. It would be antibiotic resistance, or sometimes we call it antimicrobial resistance. And this is the notion that bacteria, who we can treat with antibiotics, they're evolving resistance to these antibiotics. And antibiotics that used to work for us a year ago, 5 years ago, 10 years ago, don't work anymore. So we're facing a potential future where 20 years from now, 50 years from now, we might not have any antibiotics left. And that's a really scary thought. I mean, imagine going into the hospital for a really simple surgery, like maybe you need a knee replacement or, your little finger amputated or something. If we don't have simple surgery, do it yourself at home kind of stuff. If we don't have antibiotics, you could pick up an infection as a result of this simple procedure and you could die, because that's what happened up until the 1940s. People would get a scratch. There's a really great story that a writer, Maren McKenna, who's a good friend of mine, she wrote a beautiful piece about what would a future without antibiotics look like. And she told the story of her uncle, who was a firefighter in, I think it was New York City back in the 1920s and 30s. And in the late 30s, early 40s, he got a scratch. He was working on pruning a rose bush. Simple thing in your garden, and the rose bush scratched him. That scratch got infected, and within a couple weeks, he had died from this infection, because this was the era before we had antibiotics. That era could be coming back again. That could be in 20 years. You might not want to go in the garden, because if you get that scratch and it becomes infected, it's game over. So that's really terrifying.
Dangerous place for injuries. Also the school. I had to go on a 7-day course of penicillin after stapling my finger right up in I think it was maybe Stacy Mitchell's class 4 years ago. So antibiotics are very important, whether it's a cut or a staple or a surgery. A future without them is pretty scary.
It's terrifying,
so.
Yeah.
Any other questions? Got one maybe there.
Oh, yeah, and the stripes.
It's an embarrassing story, but really paints
Who
the picture.
hasn't stapled themselves,
Yeah.
really?
What are people trying to do to stop antibiotic resistance?
Oh, great question. What are people trying to do to stop antibiotic resistance? There's quite a few things. So one of the things that we're trying to do is discover new antibiotics. And scientists are looking for these in really amazing places. My favorite new antibiotic was discovered in mud from a field in Maine in the United States. And researchers are starting what we call citizen science projects, where they're just getting people in the community to go out and take samples of things. There's a researcher that's doing a citizen science project, getting people to look in, the soil from their backyard or the stream that runs near their house, and sending in samples so that they can discover potentially new antibiotics out there in nature. So that's one of the strategies, is find new antibiotics. Another one is convince the companies that make antibiotics to invest more money in discovering new ones. That's a bit of a tougher challenge. Another strategy that we're doing is, in public health, we like to say all the time, an ounce of prevention is worth a pound of cure. We should probably figure out what the metric equivalent of that is.
So
yeah. How many milliliters of prevention is worth a liter of cure? We want to prevent infections in the first place. So if we can come up with vaccines to prevent these bacterial infections from ever developing, that's really helpful. And if we can message around just how to live a healthier lifestyle, and it's not about, using antibacterial soaps and cleansers in this. It's just simple, washing your hands with soap and water. There's a famous quote from a Canadian physician who was sort of the father of public health, who said the soap, water, and common sense are the best disinfectants. So that's a strategy as well. And we're just looking for other creative solutions that aren't drugs and that aren't vaccines. So one example that I can think of is there's a company who, they recognize that when you go into a hospital, there's a pretty strong risk of picking up an infection, and potentially one of these antibiotic-resistant infections. And it's because you can find bacteria on surfaces everywhere throughout a hospital. So they're trying to design a coating, just like something you'd apply to the floor, and it has a really weird texture to it that bacteria don't really stick to and form biofilms or form little collections of bacteria on. So maybe it's just in how we design a hospital, and thinking about, engineers have a role to play in this. How can we use engineering to make a safer, less bacteria-ridden space? So there's a lot of cool things that we can do that just aren't all about finding new drugs.
That was such a good question.
Yeah.
And maybe a good follow-up, too, is how, as citizens, people can reduce sort of how can they contribute to this fight against antimicrobial resistance just in their day-to-day life and when
Yeah.
they're taking medication?
Yep, for sure. So definitely prevention. Just keeping yourself from getting sick in the first place is the best thing that you can do. So we don't want you to have to take antibiotics. So again, regular hand washing, not touching your face is something that we recommend people do, but it's really hard for people because you don't realize how many times in the course of a day your hand kind of automatically goes to your face. You know, if you're talking about a germ, it needs a way into your body. It's not going to sort of burrow its way through your skin unless there's a cut. It needs to be touched to your nose or touched to your mouth. So if you stop doing that, you can actually reduce the number of infections, colds, illnesses just across the board that you're dealing with. So prevention is definitely step one. And anything you can do, whether it's basic hand washing and hygiene to vaccination, do all the prevention things. If you are given a course of antibiotics, you need to ensure that you're not demanding antibiotics for viral infections. Antibiotics, anti-bio, against a living thing. Viruses are not alive. Antibiotics only work against living bacterial organisms. So if you've got, cold, flu, almost all of the time those are viral infections and antibiotics aren't going to work. But oftentimes, people say, oh no, doc, just please write me a script for some antibiotics. I know it'll make me feel better. And if the doc is stressed and needs to get to the next patient, oh, okay, here you go. So ensuring that you're only taking antibiotics for an infection that it'll work against, and ensuring if you are prescribed antibiotics, you use the full course of them. Because bacteria are really clever. If there's one bacterium, you might be infected, you might have 1 million bacterial cells in your body, and if there's just one of them that is resistant to that antibiotic, you take your antibiotic, all the ones that are susceptible die, whereas one, the resistant one, left over, and they divide, and they divide again, and they divide again, and they divide again, and all of a sudden you've got an entirely antibiotic-resistant population of bacteria inside of you. So taking your full course of antibiotics is really the best way at kind of getting every last bug out of your system. I also definitely recommend if you're taking antibiotics to take probiotics along with them too. So anybody in my family is on a course of antibiotics, ensure that they're eating their probiotic yogurt like nobody's business and taking their BioK Plus or whatever supplement it is they're interested in. Just trying to replenish your body's own microbial flora, because our bodies and the microbes that are already in there do a pretty good job about keeping the bad microbes out. When your gut, for example, it's lined with all of these wonderful bacteria that are helping you digest your food and capture energy and nutrients from that food, but they also kind of keep the bad bugs out. It's almost like your gut has parking spaces, and all of the parking spaces, when they're filled up with good bacteria, the bad guy, the C. difficile or something, comes in, it's driving around looking for a parking spot, trying to find one so it can establish infection, but when it doesn't see a parking spot, when they're all filled up with good bacteria, it's like, okay, well, I guess I'll just leave. It leaves out the back door. So those are some of the things that you can do.
I think that's really interesting to know about. Any other questions? Oh, one here.
I wanted to, on the subject of antibiotics, how many people are actually allergic to antibiotics?
How many people are allergic to antibiotics? That's a good question. I don't know the answer to that. I would check, try maybe, we have a program at BC CDC called Do Bugs Need Drugs? It's a fantastic resource for information on antibiotics, and I would check the dobugsneeddrugs.ca website. That's a question that I don't know the answer to.
Anyone else? Oh, perfect.
How will microtechnology be integrated into the future of medicine, and could it be applied to immunizations and antibiotics?
Oh yeah, excellent question. So how can things like microtechnology and nanotechnology, how is it playing a role in public health and potential therapeutics in many different, very, very cool ways? So I'll give you two examples. One that's a little more traditional and one's a little more an example of a slightly bigger technology, but still something small and cool. So the first example is new ways of doing what we call drug delivery. And one of the most important things to do is when you're administering a therapeutic, whether it's a vaccine, whether it's an antibiotic, whether it's a chemotherapy agent or something, is to get the drug to the right place in the body. And a whole bunch of work is now going into how can we use, and nanotechnology, interesting formulations of getting drugs to the right place in the right way. A really cool example, this is a bit of an older example now, but there was a company in Vancouver that designed a drug that would scatter throughout the body, but it would only become active when you hit it with light from a laser. So you would give people the drug, and you'd allow it to kind of build up in their system a little bit, but it wasn't turned on yet. So it didn't matter that it was all throughout their body. It wasn't active. But when you hit, imagine you were trying to treat a tumor, for example. You would just target the area where the tumor was with a little bit of laser light. It would wake up the drug in that part of the body, and it would go to work specifically right in that area. So with these sort of nanotechnology and microtechnology, we're coming up with smarter ways of getting drugs to where they need to be, and smarter ways of keeping them kind of inactive until it's time to turn them on and go, okay, go, do this thing. Another example, which isn't so much micro or nanotechnology, but is a cool example of small technology really opening a lot of doors, is in the work that I do, which is doing genome sequencing. So a genome is the set of genetic instructions that encodes a living thing. Everything that's alive on this earth has a genome. It has this set of genetic instructions to make a Madee, to make a Jen. And the genomes, it's a bit like a book. It really is kind of like an instruction manual. And we can read these instruction manuals. But the way we've done it in the past requires some very big machinery and very expensive machinery. So to read the TB bacterium's genome, to read the flu virus's genome, has required a lot of work. Machines that cost, upwards of $100,000, and some of them are almost as big as the stage that we're sitting on. But as a result of figuring out new clever ways of looking at DNA, new clever ways of getting computing power smaller and smaller and smaller, there's a DNA sequencer now that's about this big, and it plugs into the USB port on your computer. So whereas before, we've been sequencing DNA since 1977, and so for the last 40 years, people have been taking DNA back to the lab, running it through this really big piece of equipment. Hundreds of thousands of dollars. It's only accessible to a very small number of scientists. But now we can take this DNA sequencing technology anywhere. So friends of mine, when the Ebola outbreak was happening in West Africa, they brought this tiny little DNA sequencer, and they were taking Ebola virus every day from patients that had just been diagnosed. They were sequencing its genome, and they were looking for clues in the Ebola virus DNA that would tell them who might have transmitted to whom. And so this was in the last stages of the outbreak, where you had little bits of disease flaring up here and there, and they were getting kind of tricky to contain, but they were the key to stopping the outbreak. And the information that they got from this tiny DNA sequencer in real time out there in the field really allowed them to say, okay, I know where this cluster came from, how we're going to sort of shut down this cluster, how we're going to prevent further cases from spreading. We're going to have to do X, Y, and Z. So this really cool little tiny piece of technology that you can take out there in the field has really changed how we do public health.
Yeah, great question. There's one right there. Oh, yeah.
So when you get sick, do you instantly know what germ it is and how to treat it?
That's a great question. I don't get sick all that often because I'm a good public health person who's always washing their hands. And when I do get sick, instead of doing science on what I have, I do a little bit of sort of empiric diagnosis. I'm like, you know what?
You're not taking it to the genome sequencer?
I'm not taking it to the genome.
Okay.
Yeah, but you know what? There's a cool story. My colleagues did an experiment a while ago. They had done this DNA testing service where you send your own DNA to a lab, and they'll tell you a bunch of cool things about you from reading your DNA. And one of the things it told them was that they were probably resistant to a particular type of food poisoning called norovirus. Norovirus is really gross because it makes things come out of both ends at the same time really violently. It's like being a human volcano. It's terrible. So they were supposedly resistant to norovirus according to this genome test that they had done. But then their whole families, these two families at the same time, there's a big norovirus outbreak in Vancouver, and they both got sick. They're like, what gives? We thought we were supposed to be resistant to this. So they collected their own poop. They collected their own vomit. They brought it into the lab. They sequenced the norovirus genome, and they realized that the virus had sort of changed. The flavor of norovirus that was circulating around the world had evolved to a point where people that had this resistance mutation were suddenly, no match for the virus. The virus was able to bust through that and make people sick. So that was kind of a cool example of my coworkers, coming into work one day with a bag of something in their hand going, I don't want to know what's in that, but, do tell me when you get the results.
Good question.
That was a great question.
Hi, thanks for coming. If you had to do a 60-second public health spot at a conference for anti-vaxxers, what would you say in those 60 seconds?
You know what? I think the most powerful messages are stories. And when it comes down to vaccination, the key thing to remember is everybody wants the best for their child. But I think we've sort of lost a bit of perspective around the real risks of vaccine-preventable diseases. Our generation grew up fully vaccinated, and we don't know, the kid that had to go into the iron lung with polio. We don't know the kid that lost their hearing due to measles, because we just didn't see that. So when we can bring the conversation back to, this is a really real danger to the people you love, and there's a very simple thing that we can do to prevent it, that, I think, helps to move the needle a little bit. And it's really about the power of story and showing people that have been directly affected by this. There was a great story on CBC, I think it was about a year ago, and it was a woman, I think she was a mother to 2 or 3 children. And she'd always been a little hesitant around vaccines. She wasn't sure whether she should administer the full schedule, on the schedule that's recommended. Just didn't know. But when her entire brood of wonderful, beautiful children came down with whooping cough, something that is vaccine preventable, and it's scary when your child is coughing in a way that makes it sound like they're close to respiratory arrest. That's a really frightening thing. And that one experience of seeing somebody so close to her really changed her perception, and she went over to the sort of doing the full recommended vaccine schedule, and she was sharing her personal story with the people around her and said, look, this can happen to me. This happened to my children. This is a very, very real risk. So I think the key is stories from people that have experienced it themselves and who can really connect with like-minded individuals, parents who care about their kids, saying this is why you need to do it. A friend of mine, Janet Tobias, she's a filmmaker. And she did a beautiful film called Unseen Enemy. It's a documentary. It aired on CNN Films last year. And it's talking about where will the next pandemic come from. And the most affecting story in that show, in the film, it's about a 2-hour film. And the one story that just so resonated with pretty much everybody that saw the film is the story of a young girl, 17, high schooler, perfectly healthy, out there playing lacrosse and soccer and all sorts of other sports in Minnesota, and she got the flu. She didn't have anything like asthma, any conditions that would have made her at higher risk of complications due to the flu. But within a few days, she had passed away. And the mom had tried to revive her daughter, giving her CPR on the bathroom floor after she'd passed out while she was having a shower, and she died. And it's a simple vaccine-preventable disease. We've got a flu shot, and now this mom's campaign is all about getting other people to vaccinate themselves against the flu, saying, maybe you're not worried about it for you, but there are children, there are older folks that are at really real risk of dying, and we saw that in the States this year. We had a terrible year for flu. The deaths in people that should not be dying from flu. So really telling those personal stories is, I think, what sticks. That's a great question.
Oh yeah, one over here, I think.
And then we've got one down in front too, yeah.
Me next? We're hearing a lot more about dogs being trained to sniff out various infectious diseases like C. difficile with an astounding 97% accuracy. Could you explain how that works, and what's the future of the smell and disease?
Great question. Yeah. So I don't know if any of you have seen Angus. Angus is the cutest employee at Vancouver Coastal Health. Angus is a dog who is trained to recognize the smell of C. diff. Anybody that is a nurse or a doctor and has worked on a ward where somebody has C. diff would tell you you don't need a dog to smell it. You can tell when somebody on your ward is sick with C. difficile. This is a bacterial infection. It causes really severe diarrhea, and it does have a very characteristic odor. But we're also training things like rats to sniff out tuberculosis and diagnose TB. Yeah. So what's happening is when you've got a particular pathogen that's infecting you, typically bacterial pathogens, they need food. They're eating things and they're producing byproducts. Just like we eat food and we poop and we fart, so do bacteria eat things and they sort of bacterially poop and bacterially fart. And one of those things that they bacterially fart out are little small chemicals, little small chemical compounds, and those chemical compounds have very distinct odors. Our noses aren't powerful enough to pick these things up, but a dog's nose, it's got way more olfactory receptors, smell cells than we do. They're able to pick up these little things. So an individual who has a TB infection, when they cough, when they breathe, little farts from the TB bacteria are sort of coming out on their breath, containing these tiny little small molecules that these rats can pick up. And same thing with C. diff. There's this very characteristic odor. It might be so faint that humans can't pick up on it, but Angus, the C. diff dog, can. So it's a really interesting, using the power of animals' scent as a tool in diagnosis. And one of the challenges there is that, it took a while to train Angus. I've got a puppy right now, and training a puppy is not an easy task. So training a dog to recognize these smells, training rats
let alone a fleet of rats.
Exactly, enough rats to, sniff out all the tuberculosis in the Indian subcontinent is really challenging. So what researchers are starting to do, again, this is a nice example of how there's a place for, engineers in public health, is they're trying to develop electronic noses that do the same sort of thing, the same sort of detection, but it's one robot that does it instead of having to train this and constantly replenish a fleet of rats on leashes or dogs. So it's definitely an interesting new paradigm for diagnosis.
I think we had one here. Thanks.
Is there any explanation for the rise of the anti-vaccine movement? And is there any evidence of the damage that it's done in terms of decreasing vaccination rates and subsequent outbreak of diseases?
Yeah, great. The first part of the question, there's a lot of reasons that seem to contribute to kind of the rise of anti-vaccination sentiment. And I think if I had to pick out two of them, it would be the way health information is transmitted from person to person has changed completely. It used to be that health information would be from sort of doctor to patient, and that was it. But now, with the rise of the internet and lots of peer-to-peer communication, and the rise of sites that are offering misinformation, it's really easy to transmit incorrect information or information that has a bias to it. And people tend to respond to information that comes from their peers, sometimes more than information that comes from medical professionals. So if a peer shares something with you and it's got a particular message, whether it's anti-vaccination or anything else, you're more likely to kind of believe that information. So I think the way we exchange information has contributed to it, and as well as what we alluded to earlier, where our generation just hasn't experienced these things. So for parents that are our age say, well, I'm not sure I need to vaccinate my child against this because this wasn't going around when I was growing up. Surprise, surprise, it's because we were all fully vaccinated. And then in terms of evidence for the damage that it's caused, I don't think you need to look any further than measles and mumps rates in Western Europe. So When The Lancet published an article that I don't even want to talk about, whenever you repeat a myth, sometimes it just serves to cement the myth further. So when The Lancet published an article that influenced people's opinion in a bad way, we saw vaccination rates drop by about 10%.
An article that's since been retracted.
It's since been retracted and disproved many and many a time, but you know, that first impression, the first impression is always the strongest one. We know this from risk communication. So what we've seen are measles outbreaks with thousands upon thousands of people. This was a disease where, you know, in British Columbia, we would have 0 cases of measles per year, and suddenly we started seeing hundreds of cases a year just in the last 5 or 6 years or so. Western Europe got it really bad. They would have, you know, a few hundred cases here and there, and they've got thousands, tens of thousands of cases now. America had its first death due to measles in decades a couple years ago. So there's definitely an effect that we've seen, and it's making our public health life a lot more difficult. Like when you're dealing with something that you thought had been contained and it's back all of a sudden, it's tricky. It's very, very tricky. So there's definitely lasting damage that's being done. All we can do now, though, is just move forward and say, okay, well, how do we combat this rising tide, and how can we show people that really this is a problem? We've got an effective tool, and in this potential future without antibiotics, we need to be preventing as much as possible.
Okay,
Great questions.
So I think that we have time for one more question. I know we have so many student questions. I think that was your hand up first? Okay.
How many diseases have you studied?
Oh, cool. How many diseases have I studied? I'd say the ones that I've studied the most have been 4. Tuberculosis, influenza, measles, and the mumps. And of those, flu certainly affects the most people. And of those, I think tuberculosis is the most interesting. It's the smallest number of cases, but I think it's the most important number of cases. And I know there's going to be more. I got to work for another couple of decades, so if you ask me in 20 years, it'll probably be up to 20.
I think Rob had one.
My friend had whooping cough for like really bad, but he had already been vaccinated, and like I think 2 of my friends had already been vaccinated, but they still got the whooping cough. And
you've hit on a really important phenomenon, which is sometimes a vaccine doesn't work properly the first time around. So it's really important to understand how many doses of a vaccine somebody gets to make sure that they're as well protected as possible. So a great example of that is the measles vaccine. So when you get your first measles shot, you're a baby, you're about 12 months old, but a little bit of your mom is still inside you when you're 12 months old. So when you're a baby and you're developing, your mom's immune system is the one that's looking out for you. Your immune system hasn't really grown up yet, so you need a little bit of help from mom. So she has antibodies, the things that kind of recognize and destroy viruses and the things that we hope to raise by giving somebody a vaccine. So your mom has these antibodies, and a few of them will be in you. So if we give you your measles vaccine when you're 12 months old, about 1 in every 10 kids has just enough of their mom's immune system left in them that mom's antibodies latch on to the measles vaccine and get rid of it before you can develop a proper immune response. So that's why we like to give a second dose a little bit later on. And that way, when you're 5 years old, for example, all of your mom's immune system is gone out of you. It's just your immune system that's left. So when we give you the second dose of the vaccine, your immune system can raise the antibodies that it needs. So it's really important for us as scientists, and the advice on this is always changing. We're always using the latest and greatest science to figure out, okay, what's the best timing of a vaccine? How do we do it to ensure that you've got optimum protection? And we hope to get as close to perfect as possible, but everything in life, nothing is ever perfect. So we can get close, and we try and get as close as possible, but there will always be a couple of cases where it just didn't work the way we were hoping for. But it's better to have a handful of cases where it didn't work than thousands and thousands of cases because we didn't try.
And maybe just before we wrap up, I think a relevant concept that is important for your question too is herd immunity. And so I think it's a very interesting public health concept. So I think maybe if you explain it, and I think it's important for that question as well.
Yeah, we're going to do some math. This is the best time of the day. Everybody loves a little Tuesday morning math. So one of the things that we like to talk about in public health is a number called the reproductive ratio, which is kind of a silly term for if you're sick, how many other people will you make sick? So the higher that number, the more infectious, the more dangerous or transmissible a pathogen is. And most germs have pretty low reproductive numbers. So the flu is sort of 1.2, 1.3. So if I have the flu, I'll on average make 1.2 other people sick. We calculate these over lots and lots and lots, which is why it's not perfectly round numbers. The measles virus has a reproductive number of 20. So one sick person can make 20 other people ill. That's the highest of any pathogen we know about. And here's where the math comes in. We can figure out how much of a population needs to be immune, thanks to a vaccine, by taking 1 over the reproductive number, so in this case 1 over 20, and subtracting that from 1. And you turn that into a percentage, and so for measles, when you do 1 minus 1 over 20, you get a figure of 95%. 95% of your population needs to be immune to the measles virus from a vaccine in order for it to stop circulating. If it's less than that, it can circulate in your population and keep causing outbreaks. And that's what happened in the UK. So that's the number that we're always trying to get at. It's different for each pathogen, but that's what we as public health try and do. Figure out that number and get there.
And you can go home and look up what it is for whooping cough and figure out how many people in the community
need to be
vaccinated.
because I don't know that off the top of my head. You can teach me that.
Well, thank you so much. This has been just a fantastic
pleasure.
conversation.
Thank you all for the amazing questions.
Thank you so much.
Good job, Maddee.
Hi, everyone. I'm Julian Paquette. I'm the manager of the Salt Spring Forum. I wanted to thank you both so much.
Thank you,
and
Julian.
all of you for coming. And I just wanted to thank a few other sponsors and organizations that helped make this happen. So thank you so much to the GISS Student Council, Fraser, all the volunteers, Junin. They really worked hard on this. And thank you as well to GISS, the Country Grocer, Salt Spring Air, the Salt Spring Exchange, Antipestos, the Driftwood, Salt Spring Books, all of you for coming and everyone who made this possible. We have 2 other events coming up this week. Check them out on our website. We love students and we give free tickets to students. So like us on Facebook or check us out through our website and keep coming. Thank you.
Thanks so much for all the great questions.